Okay, so let's talk about things we've got going. Your exams are graded. I'm going to hand your exams back at the end of class. I'd like you to pay attention to the new material we're covering today rather than what's on your exam. Once you get them, there's a posted answer key online. So please look at that and then come ask me questions if you have them. So when I get up here, I kind of get grooving, and I'm going to need probably a reminder near the end of class. So we have a good amount of time to get it passed back and talk about it. Remind me at 10 minutes till the end of class that I need to hand these things back, please. Let's talk about what we have going on this week. We have a quiz on Friday. There's going to be a homework due on Wednesday at 7 a.m. as usual. We didn't have one today because we had the exam. Help session on Thursday on Google Meet, and the link is in your syllabus. And the syllabus, if you don't need your paper copy, there's an electronic copy of that online. And then I'm available Monday, Wednesday appointments, 1 to 5 p.m. You can make those through Navigate, which is how we're supposed to make all our appointments, but really everybody's been making them at the end of class. So if you want to talk to me this afternoon, come up after class and say, hey, I'd like this time. If you'd like to talk to me on Wednesday, same sort of thing. You can just tell me right after class. Questions on any of that? All right, we're about to move into chapter 4. So chapter 4 is more about electrons and atoms and properties of atoms. And the first thing we want to talk about is, so remember, electrons are the big deal in chemistry, okay? Electrons determine the chemistry, electrons determine the charge of the atoms that we're working with, and they determine the properties of what atoms bind to other atoms. So as an example of that, we talked about that. What about the electrons of the noble gases results in their reactivity? So the noble gases are right here. Noble gases are really reactive, not reactive. They're not reactive. Right, I've seen some people say not reactive. So they're not reactive. Why are they not reactive? They're very stable. Why are they very stable and tied to the electrons? Yeah.
Don't they usually like try and help out and get 2 electrons, and the other can come in with 2 electrons?
They have full outer shells, what I think you're probably getting to, right? So so if we're over here, we can have a full outer shell for helium with 2 electrons, and then after helium, we're talking about 8 electrons. It's the octet rule. We're going to see that used again and again. It had all these guys below helium. Helium has the 2, like Anton said, but everybody else has 2 full electrons for that S shell, and then 6 more electrons for the P shell. Or the outermost shell is full. And so being full is especially stable. All right, we're going to see today, we're going to talk about it. And full shells and half full shells have these special properties. But that octet rule, having the full 8, is really stable. Okay, more stable than anything else. All right, so let's talk about, what I want to start today is talk about electron shielding. All right, and when I say electron shielding, I mean electron shielding of the charge of the nucleus. Now, we've talked about, we've done these electron configuration diagrams, right? We did those, they were on the test. We weren't just doing them for the heck of it. We were doing them because they do tell us about reactivity, okay? And they're going to be important for explaining our properties we're talking about today. So let's go ahead and let's take carbon, let's say, okay? So let's look at the electron configuration of carbon.
Actually, I'm going to change it from carbon because I want more electrons. Let's do silicon. It's underneath of silicon. Okay, the electron configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, and you'll notice, no, it's 3p2. And you'll notice I'm using the, you saw me look at the periodic table if you looked up there, but really how I was doing that in my head, but if I was not doing it in my head, trying to write and talk to you at the same time, I'd be looking at a periodic table. 1s2 across the top row, 2s2, 2p6, 3s2, 3p2, and I wouldn't have made my mistake of 4 if I'd actually been using the periodic table as opposed to trying to do it from memory and write it and talking to you at the same time. Okay, so that's our configuration here. We have this thing called noble gas configuration. How would I write this with noble gas configuration? I start with neon. See, I took your word for it, and I looked at the periodic table. I'm using the periodic table. So, and then what do? I don't go to 2s2 because neon's in the second row. I go to 3s2. Yep, very good. Okay, 3p2. Okay, so we do. This is like this cool shortcut, right? You don't have to write as much, but it's actually communicating something about the structure as well. When we look at these electrons, these guys with this full, too far. These guys right here, these electrons. That's a full shell. They're full shells. So they're super stable, right? This is telling us we're using this noble gas configuration. Those are the full shells. They're super stable, right? So electrons determine our chemical reactivity, interaction with the outside world. In being super stable, they don't those electrons don't interact with the outside world. They're held close, and because they're closer to the nucleus, they're going to shield all the nuclear charge. That 1 for 1. That makes sense. Okay, so. If we look at this, how many electrons do I have here in these two shells? I've got 10, right. Guys, got to speak up a little bit. I'm old and I'm getting hard of hearing. So I've got 10 electrons in the inner shell. I'll say shells. Okay, inner shells fully shield the charge of 10 protons. All right, does that make sense? And then the outer electrons, they're going to shield charge too, but just to make it easy, we're going to say that they kind of don't. It's not true. They're shielding charge too, but they're not shielding charge as much. And so we have this concept of effective nuclear charge. And what that means is that's how much of the protons you can see, right? You can't see the first 10 protons. But silicon has how many protons? 14, right? 14, right? The atomic number. So it's 14 protons. So we can see 4 of those protons, at least partially. All right, so 4 protons left. Oh, there we go. 4 protons left. So we say the effective nuclear charge is 4. or plus 4. I mean, but it's always going to be plus. It's a nuclear charge. All right, questions on that? And in fact, I'm sorry, a better way to write that, this actually has meaning. We're not going to talk about it right now, but it's 4 plus because it's an actual charge. All right, so our equation there was number of protons minus number of inner shell electrons is equal to effective nuclear charge. And what we rather than write effective nuclear charge over and over and over again, we have an abbreviation for that, which is Z effective. Okay? And so in this picture from your book, let me make that a little bigger. They're showing that. Okay, so they're using a simpler example. They're using lithium and beryllium, but they're talking about, we've got for lithium and beryllium, our inner shell is this 1s, right? They're in the second row. So we have the 1s. These 2 electrons in the inner shell fully shield the nucleus. Over here, beryllium's 1 over. We have 1 more proton, fully shielding that. And so they're using the same equation here. They're showing that we've got here, we have 3 protons. 2 of them are shielded by these inner shell electrons. And then we essentially have 1 that we can see out here. Okay. Here we have 2 that we can see because we still only have 2 in that inner shell. And then we have 2 now in this the outer shell. Questions on that concept? Yes.
How do you understand like how many outer electrons you have?
How do you tell how many outer electrons you have? So what I recommend you do is you use the periodic table. All right. And so everything is going to be, we're going to be looking at that like this. So you can get out your periodic table if you want, if you can't see it from the other side of the room. But we've got, so let's say I've got chlorine. Okay? Chlorine has 1, 2, 3, 4, 5, 6, 7 outer shell electrons. Okay? And so it's going to actually, since for neutral chlorine, since we have the same number of electrons as protons, what we're going to have here is we're going to have 7, their effective charge is actually going to be 7 here. It's going to be 7 here. It's going to be 7 here. Okay? All right? When we think about the effective nuclear charge, what happens here once we finally get to where we have the transition metals involved is that you would count, as long as this isn't full, as long as this, the transition metal block here isn't full, then you count the electrons, right? They're out there. You would count that for the charge. But once this thing gets full, it becomes stable, and it actually, you consider it to be an inner shell. Does that make sense? Okay. So if we were looking at, let's say, chromium, what we would do is we would go, no, actually, you're going to assume that, and then once you're outside of that, then we'll go with the S and P blocks, okay? I don't know that you need to know that for this class. I'm thinking about what I saw in the book. We're going to be doing atomic trends. Well, let's do chromium anyway, just in case, okay? So chromium, what we get to then is we have argon. Chromium is right there, it's 24. Be 24 on your periodic table. By the way, does anybody want a periodic table? Nope, okay. So it's number 24. We have the electronic structure of argon, and then we're going to go, not krypton, we're going to go potassium, I'm sorry. We're going to do what row am I in? 4, 4s2 for potassium and calcium, and then I'm going to go 3d. Our d's lag by 1, our f's lag by 2. 1, 2, 3, 4. Okay, 3d4. Okay, and so what that would mean is I would have an effective nuclear charge of 6 there. Okay, but once the D's are full, they don't count anymore. They drop out. All right, so we have simple rules. Rules get, when we build on them, they become a little more complex depending on what our models are. So let's say this is chromium. How could I make my structure of chromium better? Let me draw this for you. So I've got 4s is got 1 orbital. The 3d has 1, 2, 3, 4, 5, right? I did it like this. How could I make it better?
Take one of the 4 S's and put it there.
Yeah, very good. I would take one of the 4s's and put it in a 3D, and now I have 2 half-filled shells. Remember, half-filled shells are especially stable? Okay. Details, it's more important that you can do the basic structures than be able to do the half-shell sort of things to come up with the exceptions. Okay. Questions about effective nuclear charge? Actually, let's practice calculating one. So what is, not in capitals, what is the effective nuclear charge of neutral aluminum? Which is Al on the periodic table, and number 13. Aluminum, if we make it all the way through lecture, aluminum is a great example for a bunch of things. All right, somebody want to share their answer with me? 3, yeah. Okay, very good. All right, so what I would do if I wanted to answer this is I would say, okay, not argon, neon. Neon is my noble gas, right? Okay, I'm especially going to use noble gas configuration unless forbidden because I'm lazy. I'm going to do 3s2, and then I can go 3p1. We're neutral. We have 3 electrons in the outer shell that aren't doing as good a job of shielding the protons, everything else. You could also just count over 1, 2, 3. This is going to have a 3. This is going to have a 3. This is going to be 3. Okay, that's why I have the same reactivities, because these things in the same column have similar electronic structures. Okay, it's about those outer shell electrons. Questions? Okay, another way you could have done it is you could have said, how many total protons do I have, right? Total protons is 13, okay? Minus inner shell electrons is how many neon has, right? Minus 10 equals 3. Number of protons, inner shell electrons. Okay, so there we have an equation if you want to use the equation. Questions? All right, so let's go use this for something then. So what we have though is we know that as we go across the periodic table, if I take this third row here, this has an effective nuclear charge of 1, right? This has an effective charge of 2. This is effective nuke 3, 4, 5, 6, 7, right? So what that means is those electrons in that outer shell, right, the ones that interact with the outside world and determine the reactive properties of the atom,
those electrons are seeing more and more charge as we move across the periodic table, right? And so electrons are what charge?
They're negative, and the nucleus is positive, so they're going to be pulled closer to the nucleus. Negatives are attracted to positives. And so what we see, well here, this thing just does what I just talked about. This picture shows we get a greater net effective nuclear charge as we go across the periodic table. And what that does is that means that our atoms get smaller as we go across the periodic table. I'm gonna, so we've got, I don't like their arrows, I'd rather go smaller, but so I'm gonna do that. Get smaller as you move to the right across the periodic table due to the increasing effective nuclear charge. And I'm going to do a Z effective. I guess I'll subscript it. I want you to be familiar with both the term and what it means. Whoops. I generally get lazy, and because I can type faster and I can go up to this little column and subscript stuff, I'll sometimes type out the name rather than give the symbol. Okay, so does that reasoning make sense? Why that's going on? All right, so we're going to get smaller as we go across, and you can see this. You can see this effect with these atoms here. All right, it's giving you the size in picometers, which caused me all sorts of problems last night trying to look at it because I want it to be in angstroms. But if you want to put it in angstroms, you just divide everything by 100 here. And I'll come back. I want to talk about those radii in a second, but I want to talk about the other trend here. All right, so what I'm saying is I'm not following their arrows. My arrows, let's do my arrows in yellow highlighter, I hope. All right, so it's not going to work. All right, I guess it's a highlighting text. Let me do it with a draw highlighter. There we go. My arrows are going to go this way. Or let me make them make them in pink. My arrows are going to go this way. So what I'm talking about is this pink. All right, rather than the way their arrows go. So why do they get smaller though? If you look here as well, so we've got effective nuclear charge, but if I go up in any of these columns, the atoms get smaller. Why do they get smaller? Let's take our noble gases. Okay. Full outer shell, right? The S and the P will have the same number, so we'll have the same number for that. What's the number on the shell for krypton? Let's go over here. Noble gas, krypton. Or what's the principal quantum number, N? 4, right? We just count down. 1, 2, 3, 4. Okay? So this is the 4th shell. This is the 3rd shell. This is the 2nd shell. That's the 1st shell. And if we go back and look at our little diagram they gave us with for lithium and beryllium, if you remember this, your shells get bigger. Okay? The shell in general gets bigger as you add these. So when we look at lithium here, the 1st shell is kind of here. Our 2nd shell is it's actually all of this, right? Our 2nd shell is like this, it's bigger, okay? So as you move down the periodic table, your shells, you go up in terms of what your principal quantum number is, what shell you're in, and the atoms just get bigger. Does that make sense? Okay. So once again, I'm going to I'm going to talk about the smaller direction though, because it's more useful for some of the things, most of the things we're going to talk about. And so as you move up the periodic table, atoms get bigger or get smaller because the outer shell is smaller. Okay, and in parentheses, I'm going to say a smaller principal quantum number. And that's n. All right, and once again, in terms of highlighting, that's this. That's this effect here. Questions on those trends? All right, so what we have off to our left here are atomic radii. I want to talk about atomic radii and non-bonding radii. Or we can talk about bonding radii and non-bonding radii. I'm just going to say their chart at the left. Left, yes, left. Are radii measured when an atom is bound to another atom. These are smaller than non-bonding radii. All right, so if I was to draw a picture of bonding radii and non-bonding radii, they would look like this. Let's say we were talking about, let's talk about oxygen. Oxygen is O2 in the air, okay? A stable form, a relatively stable form of oxygen is that. You light a match and you have something it can bond to. Actually, it's not very stable. But O2 is going to look like, when we think about it in a molecule, it's going to look kind of like this, where this is one O and this is another O. Okay, so we've got two spheres, and those spheres don't touch at the sphere line. You actually end up with the spheres being cut off a little bit. And so when we think about the radii here, this would be the nucleus of one, this would be the nucleus of the other, and then the radii is this. And if my art was better, these would be the same. Or I should say radii, because there are two of them. Okay, so those are bonding radii. And then non-bonding radii, if you were to take those same two oxygens and you were to make them sit next to each other, let's say you had liquid oxygen, which is a thing. I'm not going to try and make it here, but I used to at another institution where they had laxer safety rules. It was also longer ago, and the safety rules have gotten more laxer too. But I used to you can make liquid oxygen, and then you can like put Ritz crackers in it, and you light them on fire, and they essentially explode because they have all the oxygen they need is right there. So a good explosive is something that has all its oxygen in with it, and then it can burn super fast. All right. Otherwise, if you try and burn a Ritz cracker, it has to wait for the oxygen to come in. It has to wait for it to diffuse in from the air. But these are bonding radii over here, and then non-bonding radii. Let me type it instead. Non-bonding radii are the distance from the nucleus to the outer shell of the electron, the outer part of the outer shell electron. And so that would be an example of this. And here I will say radius. Questions on bonding and non-bonding radii? All right, I'm introducing these because you may hear a term called van der Waals radius. Okay, I hear it a lot in my work, where my research, where I'm doing computational chemistry. I'm not just putting it in because of that; it was in your book as well. So I've heard it all. I've heard talked about van der Waals forces and van der Waals radii, kind of all my chemistry life. Questions? Okay, that's what the two differences are there. So let's talk about sizes then of charged atoms. So when an atom becomes charged, what happens? Positive or negative, what happens? It gets bigger or smaller. But what happens? What happens with the electrons for it to become charged? Yeah, you lose an electron or you gain one, or lose two or gain two, or lose three or gain three. Okay, so when an atom becomes charged, electrons are lost or gained. And this causes the size of the atom to change. All right, we can see that demonstrated in this figure from your book here. So let's say we've got sodium here, right? Sodium looks like this. All right, so sodium has one electron in its outer shell when it's neutral. When it loses that electron, all right, so sodium, which shell, so shell is principal quantum number, which shell is that one electron in for sodium? It's 3, it's shell 3, right? 1, 2, 3 down from the top. It loses an electron. Now which shell are its, if it loses its electron, it gets the same electronic structure as neon. We step back. Which shell are its outermost electrons in? Second, right, 2 instead of 3. We just went down a shell, right? And every time we go down a shell, the atoms get smaller, right? So we see that right here. So we could say sodium and just to remind you that sodium is Na. Okay, sodium gets smaller when it loses an electron. Because then the outermost electrons are in the smaller 2 shell instead of the larger 3 shell. All right, what have we got going on with chlorine here? Chlorine. What shell are the outer electrons of chlorine in? Third, right? 3. When it's chlorine, chlorine takes on an electron, right? The stable form of it, because it wants to have the same configuration of a noble gas. It wants to have that full outer shell. It takes on an electron, and what shell are those in now? Still 3. So what's going on there? Well, and this happens the other way as well. Sodium's a nice example because it actually drops shells. But what is the Z effective here? What's the effective nuclear charge seen by this chlorine? It's going to be not 8 but 7, right? So if we want to use, we can count our way across. So remember, it's inner shell electrons, right? So everything above here is the inner shell. We can count 1, 2, 3, 4, 5, 6, 7 is the Z effective there. You could also take 17 and subtract 10 from it. Okay, so Z effective equals 7. Now when I add, remember that let's go back to our equation. Remember our equation for Z effective is equal to number of protons minus number of inner shell electrons. When I add that electron to chlorine, does my number of inner shell electrons change? So neon represents my inner shell, right? Still neon, right? So my inner shell electrons don't change when I add another electron. How about my number of protons? Does that change when I add an electron? It doesn't, okay? You can never change the protons on an atom outside of nuclear chemistry, but you can't, if you change the number of protons on an atom or an element, it becomes a different element, okay? All chlorines will have 17 protons. So my Z effective is still 7 here, but I have more electrons in my outer shell, and they push against each other, right? They're all negative. They're going to push against each other, okay? And so it becomes bigger. So for chlorine, when chlorine gains an electron, its effective nuclear charge doesn't change to compensate. And you have more negatively charged electrons crowding that outer shell. Those electrons push on each other and make the shell larger. Okay, questions? So for sodium, we had this great effect where, where we dropped down the shell, things became smaller. But if it had been magnesium losing an electron to become magnesium plus 1, you'd still have the same Z effective for magnesium. But now you have fewer electrons pushing on each other, and so the shell, it would also become smaller. Questions? All right, let's do a problem with that then. All right, so rank the following ions from smallest to largest. Let's go with oxygen 2 minus. We'll go with neon. We'll go with nitrogen 3 minus, and we'll go with magnesium 2 plus. And we're doing smallest to largest. So remember, the concept here is effective nuclear charge you want to apply. And you might draw out for these what you think the electron configuration is for each first. Okay. What was that?
They're all have the same electronic structures. They don't have the same effective nuclear charge. Like your effective nuclear charge is the number of protons minus the number of inner shell electrons. You do not consider the charges on the atom, correct? It's just the nucleus and how many ions, the charge on the nucleus, and how many inner shell electrons are in it.
Okay. Just to help you along, because I want to cover the next topic a little bit before I hand back exams. I hope you've realized at this point that if I was to draw the electronic configuration for these, they all have the same electron configuration of neon, right? Okay, so all of these, if I was to draw it out and actually give you, I could do helium. All these are going to go helium 2s, or you could just write neon. Okay, but helium 2s 2p6. So all you're considering here is the effective nuclear charge. I'm going to give you 1 more minute.
That's the reason the noble gas configuration. So what I'm saying is that they all have the same electron configuration as helium, plus what's in their outer shell, which is 2s2, 2p6. So it's a shorthand, but it also tells you what the inner shell electrons are. So we have 2 inner shell electrons.
Okay, let's take a look at this. So we have 2 inner shell electrons, right? Okay, if we want to treat it that way, or you could say we have 0, we have what? Not 2. We could say you have another 8, so 10 inner shell electrons. I'm going to go with 2. Okay, so how many protons here? 12, right? Minus 2 equals 10 for my Z effective. How many protons here? 7, right? Off the periodic table. Minus 2 equals 5 Z effective, right? Neon, how many protons? 10 minus 2 equals 8 for my Z effective. And oxygen has 8 protons minus 2, I'm saying, for the helium. So 6. All right, so I'm going smallest to largest. Which one of the smallest one is going to be the one with the highest what? What's the term? Effective nuclear charge, right? So that's what we just calculated here. So they're going to go magnesium 2 plus is smaller than, if I ask you for this on a test, it'd be great if you did either, you have to, if you do a line, make sure, and I'll probably put it in the problem as well, make sure to indicate which is smallest and which is largest. I like to do it with these greater than or less than signs. So I'm just reading these numbers. 10, that's the highest effective nuclear charge. Then there, then there, then there. So magnesium, then neon, then 6 is oxygen, okay, and then nitrogen. Does that make sense? Okay. I was very careful to pick these so that we call this, I didn't see this term in your book, but these are isoelectronic, meaning they have all the same number of electrons. All right, questions? All right, then I'm going to go, I want you to, I'm going to say stop me at 7 minutes to, because I want to introduce ionization energy. Okay. Ionization energy is the energy required to pull an electron off an atom. And I'm going to I want to insert a word there, off an isolated atom. All right, and the way we refer to isolated atoms is you take that atom and you put it out in space by itself, and we call that the gas phase. Okay, gas phase is a term they used in your book. But what it means is that we've got an atom all by itself. Remember, a gas is a bunch of particles moving around with a lot of space between them. So they're not really interacting with anything else. Okay, if we think about Z effective, right, that charge on the nucleus, what's going to make it harder, if we think about Z effective, what's going to make it harder to pull an electron off? A higher Z effective or a lower Z effective? It's going to be a higher Z effective because the higher that charge on the nucleus, the higher the charge that electron's seeing, the harder it is to pull it away because the charge is positive and electrons are negative, right? They're attracted to each other. So the higher the Z effective, the higher the effective nuclear charge, the harder it is to pull the electron out of the nucleus. Not out of the nucleus, off the atom. The electron was unlikely to be in the nucleus. Very unlikely. Okay, and so here's an example of, these are called first ionization energies over here. Okay, so the first ionization energy is the energy needed to pull off the first electron. The second ionization energy is the energy needed to pull off the second electron after you've pulled off the first. And then I'm just going to say, etc. All right, you can go third ionization energy. I guess you can probably go fourth ionization energy. It's not, at some point, it's not very relevant because it just doesn't happen. But okay. Here's a graph with first ionization energies. You notice that as we go across the periodic table, right? So if we go lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, we're in the same row. We're going across the periodic table. And as we go across, the ionization energy goes up. Okay. Does it nicely go up smoothly? It doesn't. So what's going on there? Well, it takes more energy to pull an electron out of beryllium than it does boron. Anybody have an idea why that might be?
Is beryllium close to 10?
Beryllium is not close to 10, but you've got the right idea there in terms of full shells. So this is a full S shell, right? And so it's hard to pull out of it. Remember, full shells are especially stable. So it's going to be harder to pull an electron out. Then we go up to here and we see this dip here, nitrogen, right? For nitrogen, I have a full S. Remember the P has 3 orbitals? And I have a half full P. So it's harder to pull it out of nitrogen, the same thing for phosphorus. Does that make sense? Okay, so phosphorus. So here we have half full P. Yes. Yes, thank you. Okay, I'm gonna go ahead and hand these tests back. I want to talk about that half shell thing. We're gonna talk, we'll review it briefly on Wednesday. I'm gonna hand this test back. Now, to curve the test, what I did was it says it's out of 72. When you get your test, I want you to cross out the 72, and I want you to write 66 there, because the test is out of 66, not out of 72. The answer key is posted for this. What I'd like you to do is look at the answer key. It's a work answer key. So if you don't feel like there was enough comments in here, which there weren't a lot of comments, what I want you to do is look at the work answer key and then let me know if you have questions. All right? And as I said, I'm available 1 to 5 today. Once you have your exam, you can leave. I'm available 1 to 5 today. So if you want to make an appointment to talk to me, I'm happy to talk to you.
Did you buy it? Yeah, probably get it for Trump. Yeah, that's
Right, so,
You
all of
gotta-
that,
you gotta buy
so
it.
it's out of 66 and a half.
We want to buy that.
Go ahead and cross out the 72 and add a 66.
You know what? I got what I wanted to do. I'll be there.
Out of 60.
All right, now I apologize if everybody else on this list. I mean, I've gotten down to where I don't know people's names. Layla? And once again, Layla? Madeline? Nicholas? Lila?
Seriously, $99?
Lindsay?
Like, it's no different than 100.
I miss anybody? Did not miss anybody. Okay. Yeah, you want to sign something?
Yeah.
So, yeah, I'm gonna try to do your first grade. Yeah, I'm gonna move on to your grade.
Oh, yeah,
Yeah,
yeah.
I'm gonna,
I just kinda like what
I can bring the grade up next time. Hopefully next time I won't have 4 exams. So,
and so then this,
I didn't know if you wanted to do
you like it?
Yeah, it was pretty good. It was kinda complicated.
Yeah, that was. I mean, it's hard at your level right now, but you
Yeah.
kind of get to start seeing it.
Yeah, I was trying to think how long that takes, like the time it takes to like create those.
Her simulations are super long. I went out to dinner with her afterwards, and her simulations are really long based on, they like move the molecules, and then they have to recalculate where all the charges are, and then they move the molecules and they have to recalculate. The stuff I do is really, it's 1,000 times as fast.
Yeah.
Because my stuff just says, this is what all the charges are at the beginning, and then it just runs.
Yeah.
Doesn't have to recalculate each time.
All right, thank you.
Yeah.